My name is Dr. Emily Rochette, and I am a longtime classroom teacher in science and chemistry education. At the moment, I'm working at the University of Melbourne in the Faculty of Education in Initial Teacher Education. So I have the pleasure of offering teachers professional learning in science and chemistry education and educating those fantastic people who seek to become teachers in science and chemistry education.
Nice one. And I'm Dr. James Driscoll, and I'm at Monash University. I'm in the Faculty of Science. I'm the Director of STEM Outreach. I'm also a classroom teacher as well in sciences and also in humanities as well, in geography. And we're here today to basically do some work with you as a professional development on how to identify minerals. And the reason we're doing this is because, I don't know if you found this as well, Emily, but many of the teachers that we have, certainly here in Australia, who are teaching the earth and space sciences part of the curriculum, are not geologists, and they haven't had much exposure to geology. So what we're trying to do is trying to just increase some scientific literacy around earth and space sciences.
When I was a classroom teacher, I had a very similar experience where I wasn't trained in teaching geology. I had very little experience with it, and so I don't know if you felt like this, but I felt like I was one step ahead of the students as I was learning about geology, and I often asked myself, well, why do we have to teach these particular things?
Yeah, absolutely, yeah. And we're kind of here we're going to make a whole series of videos actually regarding different parts of the curriculum. First of all, we're just going to show you where this links into the curriculum. Basically, if you look at the Australian curriculum, which in 2026 has to be implemented by all schools, we have minerals as coming under science level 8 or year 8. That's just the information there. As for North America,
generally, geoscience curricula internationally are quite similar, but you might see, I guess, different achievement standards offered at different levels or year levels for students. So what we have on the board, just to make a comparison, is an example from the Next Generation Science Standards, which are introduced in the United States. And you can compare and contrast, if you'd like to pause the video now, the content descriptions for those in the Australian curriculum, just to see the similarities there.
The first thing to do is really, let's have a few definitions and really think about how we teach this in the classroom. And so I always start with this slide. I like this slide because we said to the students, what is the earth made of? And they go, rocks. And we're right, it is, because if you look here, you can see that the earth is made of rocks. And then we say to the students, well, what are rocks made of? And some of them have a pretty good understanding, and they go, they're made of minerals. And we go, yes, excellent. And there's some beautiful minerals here. This is calcite from MoMA over in Tasmania. If you're Australian, you know about the Museum of Modern Art. They have a very nice sculpture made out of calcite crystals there. And then we ask the students, well, what are minerals made out of? And probably the easiest way to describe it is they're made of elements from the periodic table. And we generally find by year 8, students, especially here in Australia, have had some dealings with the periodic table. So it's not a great surprise to them to see this come up. So it's quite nice and simple.
When you're going to teach this in the classroom, it's really useful to think about what are the knowledge that students are bringing with them, and where are we going to take them. And of course, we know that we have the curriculum, and in Australia, it's not dictated in terms of like term 1, you'd teach chemistry, in term 2, you teach biology, and so on and so forth. So it's useful to sort of think about, how am I going to make some bridges between topics and concepts that students have already studied, and perhaps set them up for studying concepts in the earth sciences as you're teaching other units of work.
I completely agree with that, absolutely, especially, and don't just look at the science curriculum, start looking across curricula as well. So with geography, for instance, there are so many linkages between the earth and space sciences part of the science curriculum and also with the geography curriculum. And so I think it makes great sense, and unfortunately this isn't implemented in many schools, but it makes great sense for the geography and science teachers to meet, because in some parts of the curriculum you're kind of looking at the same thing from a slightly different lens. And if you can teach it in the same way but from those different lenses, and know what each subject teacher is is teaching, you can actually make sure that it's a seamless experience for the students. And multiple exposure as well is also very handy when you are in the classroom setting as well for the students.
That's such a good point. One of the things I ask myself is, how are we going to approach topics in earth science with a science lens that may be a little bit different, but at the same time complementary to, say, a geographer's lens?
And also, you do a lot of that with chemistry, don't you?
We do.
Because
absolutely.
The thing I love about earth sciences and geology or geosciences, whatever you want to call it is literally a smorgasbord of science. So you have bits of chemistry and physics and maths and biology, and you have bits of the geography coming into it as well. And especially things like climate science is becoming quite a big part now of the Australian curriculum and other curricula around the world. So let's get with it.
Okay.
And I suppose that something which is really important for students is because if you just go into a class and say, there's a rock, there's a mineral, okay, but you don't give them any context as to why it's important, you can sometimes lose students or really not engage them very well right from the start. So what we try to do is we have an image really of why we care. And there's a couple of things here for us to really consider. And that is, I asked the students, or we asked the students, so how many of you got a smartphone? And 99.9% will put their hand up. And you'll go, ace. So there are probably about 80 different minerals from the periodic table in your smartphone and in your iPad or your Padlet and in your computers. We all want the technology, but we also need to appreciate the minerals which are actually part of that phone. If we didn't have all of those minerals, then we kind of wouldn't have the technology which we have at the moment. And that's particularly important when we think about the renewable energy transformation that we need to build in order to combat some of the issues we have associated with climate change.
And I think that's a really important connection to also make to, in particular in Australia, to country. Where are these minerals being obtained from? Who is living on this land? Who is involved in that process? And some of the science as a human endeavor, socio-scientific issues that can come into play when speaking about minerals and teaching minerals with students.
And especially the sustainability lens. So the cross-curriculum priority area here in Australia is one of the three is sustainability. And I think that's a really important part that we have to get forward here. We're not trying to sell the mining industry per se here. We're not trying to say, we need to dig up lots of stuff for our renewable energy transition or for our EVs, etc. But we do need to do it in a sustainable way. And I think it's really important to actually get that concept across, not just in terms of sustainability in nature, but as you said, the indigenous angle as well. That's really important.
Absolutely.
So we actually bring in some of these little cars here. Some of the students get really into this, which is great. Oh, that wheel's almost coming off. Oh, just like a normal Tesla. And so all of these cars, we say to the students, well, what do they all have in common? Emily, your father has one of these vehicles. Which one is it?
I think it's maybe this one. So we've got Tesla in there, but you know what, James?
Yes.
I don't know a lot about cars, so I would probably need to be working in a group of people who know more than I do.
Yeah, I mean, I just bring this out really just as an engager, really. Some students are really into EVs, and just point out that these are all electric cars. Some of them are hybrids, but most of these are electric cars. And it's an important consideration. Why do we need to have mining? Why do we need minerals? Why do we need critical minerals, which is the term that you may hear spoken about? And that's an important consideration for us to think about.
There's certainly a lot of food for thought here, too. I'm just thinking, as you're talking about electric vehicles, even if I didn't know what these were, that these were electric vehicles, there's a great conversation to have about the materials that were used even to create toys like this.
Yeah, absolutely. And it's funny you should say food for thought, because the other thing which is really important for us to consider is that we need minerals for us to grow and to maintain. Now, I'm not a biologist. I just look at rocks and minerals and look at earthquakes and volcanoes for a living. But hey, even I know that we need minerals and vitamins and all that kind of thing for us to live. And so one thing you could do is actually bring in some vegetables, or you can bring in some cereal as well. And you can actually look on the label. Often we have things like iron, which is a mineral. There's minerals of iron. We can actually look at that on the packet and say, look, this is another important consideration for us to think about why minerals are so important.
In Australia, there's currently a big push toward including native plants in cooking and in food and things like that. And more I see publications in the chemistry space about the essential minerals and trace minerals that are in those particular bush foods that might help toward having a better and more sustainable food source for many parts of Australia. So lots of food for thought there as well. Sorry, I keep using
food.
that.
Hey! All right then, cool. All right, let's continue. So that's just some ideas that we've given you to try and engage students if you're looking for some ideas. So specifically, what is a mineral? Well, to find a mineral, we need 5 main components that we need to consider. Okay, first of all, it has to be naturally formed, and so we got a nice example here by the Bunga eruption in Iceland back in 2014. If we have a volcanic eruption or precipitation of a solid from a liquid that's naturally formed, we can use that as one of the definitions for a mineral. It needs to be solid. Liquids and gases, we do not consider those as minerals, and the reason for that is because the structure is constantly changing, and as such they don't have a characteristic crystal structure. So we've got an example there of sulfur and also of calcite. These are 2 solids, and these are also naturally formed, so hey, we can refer to those as mineral.
When you say naturally formed, what do you mean by that?
Well, it's something that hasn't been man-made, I suppose. Because you don't get man-made diamonds that you have formed.
Yes, right.
So it has to be a naturally occurring substance, I suppose, is the easiest way to describe that. Right, there's some other things we need to consider as well, and that is that a mineral has to be formed by inorganic processes, okay? Cannot be formed from living or dead organisms, and it cannot be a compound that contains hydrocarbons, okay? So it has to be inorganic, it cannot be organic. That's the definition for a mineral. And the last 2 things, which we kind of looked at before in a way, is that it needs to have a specific chemical composition and a characteristic crystal shape. So just to repeat, naturally formed, solid, has to be formed by inorganic processes, and it's got to have a specific chemical composition and a characteristic crystal shape. So a nice example we have there is halite, or also called rock salt. And as you can see, it's got a beautiful cubic kind of structure to it, the crystal shape. It's got a specific chemical composition, which is sodium chloride. It's inorganic, it's a solid, and it's naturally formed. So hey, we can say that halite is a mineral.
And I've just got my chemistry cap on there, James, thinking about the way we name things in chemistry and the way geologists name things. So if you've had a chemistry unit and you've taught ionic compounds, you can have the students sort of maybe make some comparisons to the geology names or the geoscience names and the chemistry names. And I have to say, the geological names confuse me and many of our students.
Yeah, I know. It's I suppose you're looking at the same thing from different strands of science, and so yeah, you're right. I mean, geologists, we tend to try and keep things pretty simple.
Do you? I would say sodium chloride is much easier to understand than halite, but something worth considering is getting students to have a look at the chemical composition and see how many of the properties of minerals differ, even though they might have very similar chemistries. Yeah.
I mean, things like magnetite, for instance, and hematite. I mean, one is kind of magnetic and the other one isn't quite so magnetic. So yeah, that's another point. They're both iron oxides, but they've got slightly different formulas. Talking of which, I think you have a beautiful piece of iron oxide with you, don't you?
I have brought one of my favorite things that is a banded iron formation. And I think this banded iron formation is probably 2.3 billion years old. And what really fascinates me about this is there's much larger samples of banded iron formation. You can see it's been polished and on one side there. There's lots of these formations in museums. Students or children and you yourselves, you can go up and touch them, but what's really sort of phenomenal to me is thinking that what we're holding is not only something that's very old, but something that is showing the evidence for the first photosynthesizing organisms.
That kind of blows my mind as well. It's like we know when, by looking at the geological record, we know when life started to exist on Earth, and in particular photosynthesis and therefore changing of the composition of our atmosphere is recorded in this wonderful, really cool piece of rock. So yeah, that's
and
really cool.
I think this one sample, you can speak about the vast timescales in geoscience. You can use it as a bridge between maybe a biology and a chemistry unit, for example. You can talk about the changing environment. And then you can speak about some of the chemistry and, why do the bands look a little bit different? What might their chemical composition be? So it's really, I think it's really quite a profound sample to use as a bit of a starter.
Yeah, and I suppose we jumped the gun a little bit then, because this is a rock, which is a collection of minerals, but I think this serves as a really nice way to bridge between different strands of science. Yeah, I love it.
And also thinking about where this is found in the Pilbara region, and that this is a region where Australia has its mining industry, and all of the discussion that could possibly happen around that.
Yeah, and the Pilbara, for those who aren't sure, is the northern part of Western Australia. Australia is a big country, and so this is the western part. The northern part of Western Australia is basically where the Pilbara is. So, yeah.
Thank you.
Awesome. Right. So let's continue with our journey. We define what a mineral is, and now what we're going to do is just to really think about why are minerals so important within geology. And I suppose the way of looking at it here is that in chemistry, for instance, one of the basic building blocks of chemistry is atoms, as it is in physics as well. Well, for us as geologists, our real basic building block of our science is the mineral, okay? And we have 6 different minerals up here, and all of these are included in the Mineral and Rock Lending Library that we at the Geological Society of Australia, we loan out to schools in order for them to really bring this subject alive. And we're going to be using a lot of the minerals and rocks from the Mineral and Rock Lending Library in these series of lessons. So this is basically very nice. It's actually an igneous rock. It's very sparkly, as you can see. Well, the 6 minerals that we just showed you are actually in this rock. And so what we will be doing is we're going to be identifying minerals using 5 basic parameters. And you'll be using that leading into the identification of rocks.
Can I hold that? That's a piece of granite, isn't it?
It is a piece of granodiorite, which is very similar to granite, but it has a slightly different proportions of 2 main minerals, which are orthoclase and plagioclase feldspar. But for all intents and purposes, it is a piece of granite.
And then the thing that I'm really amazed at is the size of it. This is not something that you'd see generally in schools, getting rock samples this large.
Well, it's funny you should mention that, because I have for you here, this is generally the type of rock and mineral kits that you have in schools. That's if you have any kits at all. Several years ago, there was a purge of many mineral and rock kits in Australia because there was a directive that any minerals or rocks containing asbestos needed to be removed. Now, unfortunately, what happened is that many people do not know what asbestos looks like, and so they just basically ditched the whole rock and mineral kits, which is quite frustrating. And that is exactly why we have put together this Mineral and Rock Lending Library. And so what we give you as part of the Mineral and Rock Lending Library looks more like this. And so as you can see, this is all of the minerals that we use, and you can see these are really nice big specimens. I can take a 1 cent coin here from, actually it's a €1 coin from Ireland. That's nice. Just as a size comparison, you can see how big these are. And all of these are available, so please send me an email and I'm more than happy to have a chat with you about how we can get these kits to you.
The reason why I mentioned that is because I think it's really important, particularly if you're replacing rock and mineral kits or you're seeking out a rock lending library that's appropriate, is because having larger samples that can solidly fit in the hand of a student are great for making observations.
And not just that, but with the rock and mineral library, we actually give you all of the same, so these are all exactly the same rock, and basically you can see they're nice big pieces, they all look exactly the same, and so if you're in your class and you have a class set of these, you are able to talk about it, and all of the students will be looking at the same rock or mineral, because sometimes you may have differences in chemistry or mineral composition, slightly different percentages. We've made sure that that is not a problem, so all of your rocks and minerals look exactly the same, so that it's very clear what the students are looking at.
I think it's also easier for teachers or laboratory technicians too.
Absolutely.
I don't know how many of you have opened a rock or a mineral kit and thought, I know what some of these are, and you have the nightmare of trying to actually sort through them.
So this is a training video for you to be able to use this actual kit. So what we do is we then try to tie minerals into the periodic table. And we show that some minerals have very, very simple chemical composition. So for instance, gold is just Au. It's on the periodic table. Some have simple compounds like silica dioxide, or quartz as it's commonly known as. Quartz is also the most common mineral that we have on the Earth's surface. And the other one is somewhat more complex. It's malachite, which is, I think I'm right, my chemistry is saying it's a copper carbonate hydroxide.
Yes, it is, and quite complex chemistry there. But again, if your students have learned about ionic compounds, you can get them to do a little bit of practice in terms of naming the elements or naming the complex ions that make up these particular minerals.
Yeah, and I've certainly gone into schools before and actually taken this in and actually had a laminate of the periodic table where I get them to actually circle where all of the minerals are, where all of the elements from the periodic table that make up that mineral. And that can be a nice little segue as well into explaining about what minerals and rocks are all about.
Also, a great bridge toward balancing chemical reactions.
Actually, yeah, that's true. All right then. Okay, so we are going to think of geology as a detective novel. So a bit of Sherlock Holmes going on here. And we are going to use these 5 physical properties in order to identify minerals. We're going to use colour, hardness, luster, streak, and something called cleavage and fracture, which is probably the hardest to comprehend, I suppose, as both teachers and students. So we will do our very best to get that very clear to you.
That's the hard one for me. Again, with very little experience in doing geology or learning how this kind of work is done.
Oh, yeah, absolutely.
I find cleavage and fracture really difficult. And I can't tell you how many videos online I've watched and things I've tried, and it's still something that is a bit elusive.
Oh, I completely agree. In fact, university undergraduates as well, I can guarantee that they have in first year, minerals and rocks is quite an important part of most geoscience or geoscience themed undergraduate degrees, and even it can be very hit and miss sometimes. So the other thing we've done specifically with the minerals in these kits is that the ones which are showing cleavage and fracture are very obvious.
Okay.
And so it's a really important thing to do, because you can't just give them a piece of mineral and go, oh yeah, you can see those 3 cleavage planes, and the kids will go, the students will just go, yeah.
It's got to be very clear.
Oh, absolutely.
And it's not, can't you see it there? The students need to be able to identify it. So best to maybe distill the samples that you're offering students at this stage to make sure that they're samples that are best placed to help them better develop those skills.
And that's one thing we also do, is that whenever we're doing this in schools, we make sure that we don't just give them the whole kit in front of them. You have to make sure that they're focused on the exact property you're looking at, the exact mineral you're looking at, or the rock. And so we'll be doing this as part of this PD session. Colour. We spoke about malachite before. It's beautiful, almost like acid green colour. Malachite is probably one of my most favourite minerals that we have, that copper carbonate hydroxide. And another mineral which is quite common that people can identify is pyrite, or iron sulfide. And it's got that beautiful, brassy, almost golden colour to it. It's got a metallic look to it as well. And so colour can be really useful. And I've got some malachite here, beautiful green colour, and I've got some pyrite here as well. And as you can see, these are really obvious colours, and they look exactly like the mineral they're supposed to be. It's actually quite interesting. Well, pyrite, it's also called fool's gold, is the colloquial name for it as well. And the reason it's called fool's gold is because certainly in many of the gold rushes, whether here in Australia or in California or up in Canada, many of the gold rushes involved people finding this beautiful iron pyrite and getting very excited because it kind of looks a little bit like gold, and it's sparkly and shiny, and it looks like it should be worth lots and lots of money. And they bring big wheelbarrows full of this iron pyrite down to the big cities, getting really excited. We found all of this gold, and then they find that actually it's just iron pyrite, and it's kind of worthless. Gold actually in its natural state is actually quite a dull colour. It's only when we have wedding rings or we have jewellery that they kind of buff it up to make it look quite nice and beautiful. But in the real world, it's quite a boring kind of looking mineral, which is interesting.
Absolutely. And I'm just thinking how you mentioned the gold rush, which is something that, I mean, in the state of Victoria, where we are in Australia, it's quite an important part of Victorian history. And thinking about, well, you know, if you know that the history teacher is doing a unit about that particular time in history, perhaps you can do some collaboration.
Yep, I agree. As you can see, colour. Colour can actually be a really good indicator of what a mineral is. But we as another engager, we basically take these 6 minerals. So we've got the 6 minerals here, and we put them into the little glass jar here, and we ask the students or the teachers who are doing PD, we ask them to look at it and tell us how many different types of mineral are in here.
Oh, let me have a go.
I'd
say, okay, I'll just move that one over here. 1, 2, 3, 4, 5. I'd say 6 if we're looking just at the color.
But are we looking just at colour? The reason being is that we just have 6 different minerals here. It's really to show that colour cannot be a great discriminator between different types of minerals. And so you're right, there are 6 here, and what's interesting is 6 of them have different colours, okay? So you get the students to have a look. We also get them to use a hand lens here. So let's show you how to use a hand lens. So often you'll see TV shows like Silent Witness and CSI. I'm showing my age there, using Silent Witness as a...
Yes, you are.
But what you'll notice is that you often see, you know, the forensic scientists start looking around and doing stuff, and then they'll go like this. They'll go, he did it. Okay, that's not how you use a hand lens. You can't see anything by doing this.
No.
What you need to do is you hold the hand lens, and it can be either way, because it's got 2 sides to it. It doesn't matter which side you use. And you hold it to within a few millimeters of your eye, and then whatever you're looking at, you bring it into focus. And it's typically around about there. Perfect. And it's now that I realise I need to cut my fingernails, and that's how you use a hand lens.
Can I ask a question about
Yes.
that? Just because lots of our students and teachers will be wearing glasses, just like me. Do I leave my glasses on?
No.
I'll take them off.
Oh, sorry, yeah, keep glasses on.
Keep glasses on.
Do not need to take glasses off.
So up to my eye, and
Yep.
then I'll take the sample, just
Yep.
bringing it carefully into focus there. Oh, beautiful. I don't... See, it's going to be hard to get this out of my hand now.
That's how you use a hand lens. So now, we do supply hand lenses in the kits. Alternatively, if you're at school and you don't have hand lenses, use a magnifying glass, I suppose.
I've used magnifying glasses in the classroom to a great effect. And if your schools or your areas allow mobile phones in the classroom or tablets or something like this, students can get some wonderful photographs.
Oh, absolutely.
Just using a tablet and a magnifying glass.
Yeah. And even though some schools use microscopes as well. So
Absolutely.
So that's another option. So that's how we use a hand lens. And so what we do is we then get the students to have a look at these minerals, and we get them to have a look at it and go, do they look similar? Do they look different? And then we say to the students, okay, so you've all had to think about this, give them a few minutes, and then we say, okay, so if you think there's 6 different types of mineral, stand up. And so half the class will stand up. And you go, ace. And then you go, okay, if you think there's 5 different types of minerals, stand up. And then we go all the way down to 1. And then we reveal the answer. It's a big reveal.
I would now that I've had a look at some of these and knowing what you've just said, I think I would sort them a little bit differently.
Okay,
so
let's see if you can sort them a little bit differently now.
I'm thinking of sorting them almost along some sort of spectrum, like this. And the reason why I'm saying that is because we're speaking about color and things like this, and I'm gonna be a bit cheeky and say, well, I can see this one is very lustrous. Compared to those ones.
Yes.
And I think maybe when I have a look through the hand lens, I can see some similar shapes in between these, and I just group these. Learning a little bit more and then perhaps changing the way I choose to classify things is also a useful classroom pedagogy as well.
Yeah. Would you like to know what the answer is?
I do want to know the answer, as I'm sure the viewers do as well.
That's it. Oh, there's 2 different types of mineral here.
2?
2.
Okay.
We've got our wonderful pyrite, fool's gold, which we spoke about before, and it's just that beautiful. And I love the way you use the word lustrous.
Okay.
And when we come to luster, we'll see why that's important, okay? But the other 5 here, these are all boring bits of quartz.
Are they? So they're all quartz,
Now-
silicon dioxide.
They're all silicon dioxide. Now, what they have is they have very slight different ways of forming, okay?
Okay.
So let's start off. So some of these are nice and simple. This is the usual type of quartz you see. It's almost like this sort of like transparent or see-through, maybe a bit opaque. And this is the typical glassy or vitreous quartz that we have, okay? Then we have this, which is smoky quartz, which many of you will recognize. Smoky quartz here is just quartz. It started off as this, and what happened is it's in close proximity to maybe a granite, which has lots of potassium or uranium or thorium within it, because granite tends to be quite radioactive. And so what we have is that the crystal lattice is damaged, and we end up with smoky quartz.
So it's like in chemistry, we'd say maybe an impurity.
Yes, that's a really
Okay.
good way of putting it, because the other ones we have here are also impurities. So we have amethyst here, which many of your students will recognize, amethyst, and also rose quartz here, which has got, it's a rose color, so it's called rose quartz. So impurities of iron and titanium give them those 2 different colors. And then if I heat that up to about 450 to 600 degrees Celsius, I get citrine, which is this like orangey, yellowish color. So it's citrine. Okay?
So you're changing, so through heat, you're changing the chemical structure, and that affects how light reflects off of that and how we perceive it.
Exactly. And so basically, those 5 are all quartz. So those of you at home who are playing along with this game and guess those 2 different types of minerals, then you are correct. What we tend to find is that some students in the class, especially year 8s, are kind of into rocks and minerals already. Maybe their mother or father or parents or guardian or older brothers or sisters, maybe they will find that crystal healing is pretty cool. And if that's the case, then they automatically go for the citrine, because citrine apparently is supposed to be very good for wealth. I've been carrying this in my pocket for many years, and I still am not very wealthy. So
I think we need to do some more scientific studies on that
may be a little bit of pseudoscience there, but hey. But yeah, so basically we use that as an engager to get them looking with the hand lenses, to get them start looking in detail at the minerals. So the big crux of this is that we have vitreous quartz, and then we have all of the other citrine, smoky quartz, rose quartz, and amethyst. All have exactly the same chemical composition of silicon dioxide or SiO2, but there are impurities, or the crystal lattice has been damaged by radiation. And that's why we get those beautiful colors.
Fantastic.
And in fact, if you are using the rock and mineral kits and you're actually looking at these, you'll notice that all of these minerals here that we have, the 5 minerals, actually look quite glassy. They actually look like glass, and we'll get to that, because that's an important thing that we can notice as well. Let's now look at our second property. This is Moh's hardness scale. Professor Moh, he came up with this hardness scale, and with the rock kits we actually include all of these different items that you need. I'm just going to put them out there.
Very simple items, right?
Oh, absolutely. We've got a little fingernail here, okay? Then we have our copper coin, or, you know what, recently I've been suggesting that schools use copper tubes from just a hardware store, and I'll explain why in a moment. We have a glass plate here, just a normal glass plate, and we have a streak plate. Now, we use the streak plate for one of the properties called streak, and I'm only introducing this now because there's a specific reason why we've given you the hardness of a streak plate. I'll talk about that in a moment. But for the purpose of a hardness, we use these 3 main things: fingernail, copper coin or copper tube, and a glass plate. Okay. So what we've included here is we have your fingernail has got a hardness of between 2.5 and 3. The copper tube or copper coin has a hardness of 3.5. The glass plate has a hardness of 5.5 roughly. And as I said, we're not going to use the streak plate specifically for hardness, but we do need to know that it has a hardness of between 6 and 6.5. And again, when we come to streak, we will explain why it's important.
Your fingernail is the softest
Correct.
tool on that scale.
Absolutely.
Okay.
Now, unless you're Wolverine, which would have okay, unless you're Wolverine or you have acrylic nails, that's a really important thing. If anyone has acrylic nails, probably best not for them to be using their nail as a hardness test, because it does not have a hardness of 2.5 to 3. Now, it's always a bit confusing. Some of the minerals we'll show to you today have a hardness of around about 2.5 to 3.
Okay.
But because we've all got different hardness of our fingernails, some might have harder fingernails than others, it can sometimes cause a little bit of confusion. So that is the number one spot I will say where confusion lies, is that we've been using fingernails for 100 years for hardness, but we just need to be aware that some students have harder nails than others. Okay. So we'll discuss that later when we're looking at some different minerals. So the reason why some schools prefer copper tubes or copper plates to a coin is that a coin kind of has quite a few little ridges on it, and it's much easier to see the mark on a copper tube or plate than it is to see on a copper coin. Okay. So that's one reason why. And you know what? It's some countries don't even have copper coins as part of their currency anymore. Like Australia, for instance, we don't. I think the US does. Does Canada have?
Oh, I haven't been there in ages.
Okay, no idea. But Eurozone does actually have copper coins. So yeah, that's the main reason. And a glass plate. This is really important, okay? Some schools seem to think they need to buy glass plates every year. I disagree with that. I mean, this has been well used, this particular glass plate, but there's still lots of areas on a glass plate that you can actually use for hardness. And so I would say if you're replacing your glass plates every 5, 6, 7 years, that sounds about right. You don't need a new set every year. Hardness scale, you can see there it goes from 1 all the way down to 10, where 1 is talc and 10 is diamond. We've also given a chemical formula there, which is quite useful. Within the actual rock kits that we give you, we include talc, calcite, quartz, and orthoclase feldspar. We are going to, in a moment, use talc and amethyst to demonstrate hardness. But I just wanted to quickly point out this. It is a logarithmic scale. The absolute hardness is logarithmic. It is not a linear scale, okay? So the hardness between a talc and a gypsum, which is 1 and 2 or most hardness, gypsum is 3 times harder than talc. However, when we look at diamond and compare it to talc, even though it's only a scale of 1 to 10, you'll notice that the absolute hardness is 1,600 times harder than talc. When we're taking this into schools, we don't include that information per se, because in year 8, obviously, many schools, maybe different in your country, but many schools don't actually have exponential or logarithmic scales mentioned in the curriculum until after year 8.
I think that's a really useful thing to reflect on, James. In particular, one of the things that I often think about as a chemistry teacher is that we often see graphs that are linear, and students can become quite familiar with that. So when you're introducing other logarithmic scales, like the pH scale, for example, you might want to come back to something like this. Again, minerals, there's lots of chemistry in there, and maybe you can do some of the teaching about logarithmic scales as a bit of a revision if you're going to teach the pH scale a little bit later.
Yeah, it's actually interesting. Before COVID, it was actually quite interesting. Not many students had really had that much experience, especially in middle school or in the Australian system up to year 10 kind of thing. They hadn't really had much exposure of why logarithmic charts are important and what they actually look like. And then COVID hit, and kind of like displaying information on a logarithmic scale makes more sense when you're talking about small numbers to suddenly really, really big numbers. And so COVID was actually, it's obviously a bad thing, but it's actually for graphic literacy. It's actually quite a good thing, because it's got people to start thinking what the data being represented actually means.
Absolutely. So there might be different representations that you can include in your teaching that students may already be familiar with, and then as a bridge almost to introduce other representations that are similar, but talking about other scientific concepts.
And maths. Yeah, we love maths. All right, cool. So we are going to look at hardness now, and we are going to use our glass plate, and we're going to use our fingernails, and we're going to use our copper coin / tube / piece of copper.
Okay.
All right, and we are going to use 2 different minerals. We are going to use amethyst, and we are going to use talc. So let's look at these two minerals. And before we even do the hardness, I want you to actually see what they feel like.
I think it feels really soft, and as I'm rubbing my fingers around it, I can almost feel some kind of residue.
Yeah,
coming
especially
off.
when you think it feels soapy. It
Yeah.
really feels like, it just doesn't feel particularly pleasant. It's a bit greasy, a bit soapy. And some of your students might go, it feels like talcum powder. And they would be right, because talc kind of is one of the constituents of talcum powder. So we've got some talc here. It's a bit greyish. It's not the most beautiful mineral, but it's actually a really good mineral for hardness. And then we have a piece of amethyst. So they're the two minerals that we're going to use for hardness to demonstrate how we use the equipment. And the first thing to point out is that talc has a hardness of 1, which we know from Mohs hardness scale. So the way we do this with students is we start from the bottom upwards. So we'll start with our fingernail, then we'd go to the copper, whatever you have, and then we'll go to the glass plate. Okay, so remember, they're the 3 different pieces of equipment we're going to use for hardness. So, do you want to take a piece of talc?
Okay.
And what I want to do is take your fingernail, and I want you to see if it scratches it. Okay? Oh, look at that. Nice big scratch. Did yours scratch as well?
Yeah, I can absolutely see that.
Perfect. Now notice how easy it was as well.
Yeah.
Okay, so what we can do if you had a student who was looking at an unknown mineral and they'd just done that, what you can say to the students is that the hardness is less than 2.5 to 3.
Okay, and that's one of the questions I was going to ask, because we wouldn't offer these minerals to students and say, here's the absolute hardness, go and prove it.
Yes. Correct.
We might say, can you order the minerals in terms of hardness based on the testing that you're doing?
Yeah, absolutely. Okay. Yeah, so what we do is part of the rock mineral kits that we have 5 unidentified minerals which we ask the students to identify based on the properties which we are discussing at the moment.
Okay.
That's exactly how we do it. And it's a really good way of doing that, because some of them might say, it's talc, it's got a hardness of 1. And it's like, well, no, that's not a scientific investigation. You're reading from a chart. What we want you to do is do these tests to see whether or not they can help you with the hardness. So if a student says to you, look, my fingernail scratches it, it's got to have a hardness of 1, that's an incorrect answer.
Right.
If your fingernail is scratching the mineral, then it has a hardness of less than 2.5 to 3.
So less than the hardness of your fingernail.
Correct.
Okay, got
Perfect.
it. Great.
Now the next thing is, if your fingernail scratches the mineral, that's it. You do not test it with a copper coin, because obviously the copper coin's got a hardness of 3.5. Your fingernail's 2.5 to 3. Yeah. There is absolutely no point. All you're going to do is disintegrate the mineral. So what we tell the students is, if your fingernail scratches it, period. 2.5 to 3, less than, perfect. Okay. Awesome. So let's now try our amethyst. Okay. Awesome. So let's take our piece of amethyst. I'm just going to take the talc away.
Okay.
There we go, amethyst. Okay, so the first thing is, what do we do?
I'm going to use
Dr.
my fingernail
Rochette?
to try to scratch the amethyst.
Awesome. Let's see if that happens. Anything?
No.
Now, what would you do next?
So if I look at what we know in terms of the hardness of our tools, the fingernails, the copper tube, the glass plate, the streak plate, I'm going to take the copper coin or tube and then try to scratch the surface of the amethyst with that.
Perfect. Let's have a go. Now, this is interesting, because what you might notice now is a little bit of residue from the copper coin is going on the mineral, which does not mean that it's scratching the mineral. It's showing that the mineral is actually harder than the copper coin. This is why I mentioned that it might be good for you to have a glass plate, because what you can do now is you can take the mineral and see if it scratches the copper coin. And as you can see there, yes, it does.
Oh,
very
yes.
nicely. A good thing to point out is, because it looked like originally on your piece that it had scratched the amethyst, but all you had was a residue of the copper coin on your piece of mineral.
And I can see that coppery a sort of color coming through,
Yeah.
which I'm a little bit suspect because I know I probably wouldn't see that with everything.
Yes.
But
Yeah.
it's very telling.
And this is why basically I'd suggest that something with a plain surface, like a piece of copper tube or a piece of copper plate, might be better than using a coin.
I see.
So, yeah.
Yep.
So if the copper coin is scratched by the mineral, what's the hardness?
So if the copper coin is scratched by the mineral, I would say, I don't think I could give you like a number, but I could say that the mineral is probably harder than 3.5.
Perfect. It is harder than 3.5.
Okay.
Do you think we might be able to constrain it even further?
Yes, because we have a glass plate.
What many students do is they do this. They go, glass plate, and they go, scratchy, scratchy, scratchy.
Right.
That's not how we do it.
Okay.
How we do it is we take a piece of the glass plate with one sharp movement. Perfect. Oh, and we can see quite clearly. Well, you can't, unfortunately, at home, but if you had a glass plate, you would see quite clearly. You can see there is a scratch on the glass plate. Wow, what does that mean about the hardness?
So this amethyst was able to scratch the glass plate with a
Yes.
hardness of 5.5.
Correct.
I would say the amethyst is, its hardness is greater than 5.5.
Perfect.
Okay.
That's right.
Okay.
Now, and that's when we stop. Because we know the streak plate here has got a hardness of 6.5. But, and this is where it becomes interesting. If I take my mineral, now we know that amethyst has got a hardness of 7 because it's quartz. If I take my mineral and then do exactly the same procedure to the streak plate.
Is it worth mentioning to say that this tile is not glazed?
Yes, yeah,
Okay.
yeah. And we'll talk about that when we come to streak. But yeah,
Okay.
that's a really good point. This
Yeah.
is an unglazed tile. If I do this,
I don't see clearly. Oh, okay, yes.
it just
Yeah.
scratches it. Now, but the point is that the students may say, "Oh, it scratches it," which is like great, yay, okay. But the scratch, it's scratching it, so it's more than 6.5. But all you're doing is you are damaging the streak plate.
Oh,
And so this
okay.
is why, and especially when we come to streak, I'll explain in more detail why we don't use, but we'll look at this again when we come to streak.
Yeah.
But we don't use a streak plate if the mineral scratches glass. We know it's harder than 5.5. We then stop the process. We don't use the streak plate.
Okay.
There is a reason why we need to know the hardness of the streak plate when we come to streak, but we don't use the streak plate for hardness.
So
All you're doing is destroying the streak plate, and that has big implications when we're looking at streak, because streak is literally what is the colour of the ground up mineral.
okay.
And if you're using a hardness of more than something which is harder than glass and harder than the streak plate, instead of getting a ground up mineral of the ground up mineral, all you're getting is a ground up plate here.
Okay,
And it's giving you a
yes.
false colour. Okay? But let's talk about that when we talk to streak.
So what you're saying is really we've got 3 tools that we're using to create almost a relative hardness scale.
Perfect.
And when we're trying to identify the minerals that you've carefully curated in the kit,
Yep.
we're only going to use these and we can say, this is softer than that,
Yep.
than this, and we can maybe give them a range of hardnesses within 2.5 to 5.5.
Yeah. So
Okay.
I suppose one way we could do this is we could say, okay, well, if my fingernail scratches the mineral, then we know it has a hardness of less than 2.523.
Okay.
Okay?
Yep.
So if my fingernail scratches it, it must be less than 2.5 to 3. If my fingernail does not scratch it, but a copper coin does scratch the mineral, we know we have a hardness of between 2.5 and 3 to 3.5.
Yep.
If then we take a glass plate, and if we now have it that the copper coin scratches it, but it does not scratch the glass plate, we know we have a hardness of between 3.5 and 5.5. And if it scratches the glass plate, we know it has a hardness of greater than 5.5.
So it's really important to be clear whether the tool or the mineral is doing the scratching when students are articulating the relative hardnesses?
This should be what your students are recording.
Okay.
They won't know the absolute hardness in terms of Mohs hardness scale because they need to identify the mineral first. At the end, when they've identified the mineral, and you can say, yay, that's correct. It's got, we had a piece of this mineral here, which is that beautiful amethyst. But if they had that and they said it's got a hardness of greater than 5.5, and then they were correctly identifying its amethyst or quartz at the end, you can say, oh, we actually know the hardness. It's one of those 10 index hardnesses, and you can probably say to them, well, you could probably record it as a 7 now because of all the 5 different properties you've tested and you've managed to get the right mineral. Excellent. But for the purposes of the student assessment, we would have those 4 different categories.
And then you can reflect with the students about why hardness is important, and what it means for a geologist and what it in fact means for our everyday lives as we source these minerals and incorporate them into the tools that we use.
Awesome. So that is hardness. Luster. Luster is literally, Latin for light is lux, and so luster is how does the light play off the surface of the mineral you're looking at. And one of the easiest ways that we've been doing at university for teaching undergraduates is we say to them, well, if you're on the phone to your mum and you are trying to describe what the mineral looks like as the light's coming off the surface, how would you describe it? That's probably the easiest way we do it, okay? And there are different ways. I mean, look, many minerals are shiny, okay? We try to steer away from shiny because shiny is not very descriptive, and so we try to use things which are a bit more specific, okay? So one of the things we can do is we can say that a mineral has a metallic luster. And we've seen the pyrite before, and the pyrite, you would look at that and think, oh, it looks like a piece of metal. So therefore, we refer to it as having a metallic luster. With the quartz, now we've seen many different varieties of quartz. We've had citrine, we've had rose quartz, amethyst, normal vitreous quartz, and smoky quartz. Now, it almost looks like glass, and that's pretty obvious because glass is actually made out of silica.
Okay.
Yes.
So are we talking? So we're talking about the different language to describe
Correct.
lusters. So metallic versus glassy, vitreous, and if a student were to say, "Oh, it's shiny," that's our cue to really say, "Well, what do you mean by that?"
Yeah, absolutely. Yep.
Is there a scientific way of expressing what you're saying? And so I think. I just want to sort of say that, remember, if students are using colloquial terms, it might not mean that they don't understand the science. They could have a very good understanding of the science, but they need to be scaffolded toward using the language of science to express themselves clearly.
Oh, absolutely, yeah. And so what we do is when we're actually going through, this is a similar presentation that the presentation which we're giving you as a PD is basically the same as what we give the students. The only thing we don't include are the 5 different reasons why a mineral is a mineral. We just think that's a bit of overkill for students, but it's good for you to know as a teacher. Maybe you'd like to keep that in. It's completely up to you. But certainly this is the way, this is scaffolded, this whole PD is scaffolded how we would teach this in the classroom. Because you're keeping the students focused, and you're keeping them on point, basically.
That's certainly one of the questions I like to ask myself when I'm planning a unit. What is it that I know now that I don't yet want the students to know? For a variety of reasons. Maybe that's at the point of readiness that they're at, or that perhaps something might be very interesting to me as a science teacher, but is not of use to the students at this point in time. So what do I know now that I don't yet want the students to know?
And actually it's really interesting because some students are really into this. They're really into rocks and minerals, and they will have their own little mineral rock collection, and it's quite beautiful to see. It's quite cute to see. But what you'll find is that they may even know more about rocks and minerals than you do. And so if you're forewarned and you have this basic comprehensive literacy that we're teaching you about geosciences, it will serve you well.
And on that note, if you've got students who are bringing in samples of minerals that maybe they've collected on holiday or around their local area, I know that the geoscience community is just a wonderfully helpful and friendly community. You can always reach out to maybe your local university or other educational institution and say, oh, can you help me identify this, or can you help our students identify this? We're just curious.
Yeah, cool. All right, so we looked at metallic, we looked at glassy, that's another term. Another term we can use is pearly, and feldspar, for instance, which is, I think, is the second most common mineral on the Earth's surface. We can refer to it as being pearly. It looks like a pearl. Now, I was in a school recently where I was trying to explain this to students, and I thought that students really wouldn't understand what pearls look like, and I was trying to explain it might be what your grandmother or your mother wears, and some of the students berated me and said, of course we know what pearl looks like because pearls are back in fashion apparently.
Absolutely. And there's several of our students come from international and come or even local where there's a pearling industry.
Yeah, absolutely. So I was surprised that they knew what pearly looked like, and I was quite happy because it meant I had less to explain to the students. So we've got metallic, we've got glassy, we've got pearly. Now, the last one which we're going to put up, and we are going to look at this mineral, is fish scale. And that sounds a bit weird. It's like fish scale, luster, and we will look at that when we look at that particular mineral.
That's really surprising to me because as a chemistry specialist, I really would only think of luster in terms of metals. So having these new words, fish scale in particular is new, pearly and glassy or vitreous, that's just opens up a whole new language for how to describe materials.
And until probably about 10 or 15 years ago, here in Australia in particular, maybe 20 years ago, there was also a luster terminology that we use here in Australia, which some minerals actually look like seaweed. And so we actually use that now as a term for luster because it looks like when the light shines off it, it kind of looks like seaweed. And we will look at that mineral too. And so when students come out with terminology, which may not be exactly what you expect, but it perfectly describes how the light plays off the surface, I think that is fine. That is good. It's good that students are using their terminology in that way. So.
And we talk about a similar use of terminology when we're doing things like flame tests in the chemistry lab. You know, if a student is using a particular analogy like apple green or something like this compared to something that maybe a chemist would use, again, just remember that you can understand it, and they're developing a classification system that may not be unlike what we would use in science.
Yeah, absolutely. So they are some of the major terms that we use when we're talking about luster. But as I say, if you've got students who have something slightly different, that's fantastic. Okay? Streak. First thing to point out is that streak means the colour of the ground mineral. Okay, the streak plate is literally just an unglazed porcelain tile. Okay. Now you can buy porcelain unglazed tiles cheaply from your local hardware store. There are geological suppliers which give you streak plates. Okay. Personally, I think it's easier and cheaper to basically just get some unglazed tiles from the local hardware store. But we also do have these in the, everything you see is included in the rock and mineral kits. So first thing we want to do is also point out, actually you can get black and white ones. I personally just always use the white ones, and I'll show you a little tip how you can basically see any color of material using it. This little trick I'll about to show you. So the first thing we want to do is remind our students what is the hardness of the streak plate. So the streak plate is about 6.5, okay?
So this is the known that we would give to students.
This is the known.
Yeah, okay.
And in fact, when as part of the kits that we give out, so the presentation comes as part of the kits. We also have worksheets, both the teacher copy and the student copy. So, and one of the first questions asked is actually list the hardness of these 4 items. And the reason we do that is that they can always then refer back. When we're talking about hardness, we can say, well, question 2, when did you put the hardness down? And it's a nice way just to have that repeated learning, repeated exposure, so they remember what these are, rather than having to go backwards and forwards with the presentation. So the really important thing here is that it's the colour of the ground up material, okay? Now, I'll put some up here. We've got galena, we've got hematite, and we've got gold. Now, I'm not going to use my gold ring to basically see what the streak colour is because I'm going to disintegrate my wedding ring.
Because we know that one of the properties of pure gold is that it's very, very soft. So I would not be using your wedding ring as a sacrifice.
Well, I think I was about to say I'm very classy, so of course I wouldn't have a gold-plated ring, but I think you are correct. It is a gold-plated ring. And also, you don't want to be using it as well because you're just disintegrating your gold ring, and your partner probably wouldn't be very happy. So I am going to bring in a lovely piece of pyrite. So I've got the pyrite here, and the way that we do the streak is we take the mineral, no scratchy.
Okay.
No scratchy. We want to do it in one fell swoop.
Oh, wow.
Magic. What colour's that?
I'm surprised because the mineral
Yes.
itself is very lustrous,
Yes.
a metallic luster, I should say.
Yes.
And this is sort of like a dull grey charcoal.
Yeah, it's almost dull.
Streak?
Yeah, dark grey, blackish, and pretty dull. That's because this is the ground up mineral.
Right.
Iron sulfide, basically pyrite, gives you this streak, okay? Now, pyrite has a very obvious streak colour, okay? And I can see that really clearly on here. But if I had a black streak plate and I used this, it'd be quite difficult for you to see.
Yeah.
Okay?
Yeah.
So there's a little trick we can use.
I think I know where you're going with this.
But before we show the trick,
Yes.
let's try a piece of calcite, okay? So what I'm going to do is, first of all, I'm just going to make sure that there's no dust or ground up mineral on there.
Okay, and we can still see our pyrite streak
We
quite
can,
clearly.
and you can see it on the hands
Yeah.
as well. This is an important note, is that whenever you finish this particular lesson with your students, you always get them to wash their hands.
Yes.
Okay.
Yeah.
All right, so let's take our piece of calcite and let's do the same thing. Oh, it's a bit difficult to see, isn't it?
I can just see some powder that's sort of come off, and I
Yeah.
think it looks very creamy, almost like the same color as the plate.
It is indeed. And so what we're going to do is we do this little trick. Take
Okay.
your finger,
Yep.
make sure it's nice and clean, and just rub it over the top, like that. It's white. So it's actually
Yep.
quite difficult to see on the background. So this is why I'm saying don't worry about getting a black and a white streak plate. Just basically use the white one because it's cheap and easy to get hold of.
Yep.
And just do that little trick where you put your finger over the top and see
Yep.
what the colour is.
Okay.
And it's very clear that it's white. Yeah?
Ah, fantastic.
Yeah. Now, sometimes what you'll notice is on my streak plate, I've actually got a piece of the calcite that's actually broken off, and you've got just a little piece of calcite here. What's important to note is that isn't ground up. That's just
No.
a small piece of the calcite crystal which has fallen off. It's not ground up. So when people see that and go, oh, look, it's shiny and it's like clear, that's not the powder. This is the powder that we have here.
This makes me think about when students are learning about evaporation as a separation technique. And if you're using something like a copper sulfate solution, where the copper, if you show them large copper sulfate crystals, very blue sort of in color, and the solution, of course, is a beautiful transparent blue. But then when you do the evaporation, the crystals that form are so small that the substance then appears as almost like a gray white powder. And the students will say, oh, well, that can't be copper sulfate. Add a couple of drops of water, you'll see it turn blue again. But what I'm really getting at here is we're talking about crystals, we're talking about size. And the size of the crystal will affect the light that is reflected and how you perceive it.
Yeah, good point. With this, you'll see that after a few times, you'll get this becomes quite dirty. The easiest way to clean it is literally you put this into a tub of water with some washing up liquid, leave it for about half an hour, and then just scrub it with a scrubber. And basically you get it a nice, near clean streak plate again. I mean, we want to try and be as sustainable as possible. So when I tell you that glass plates don't have to be replaced each year, streak plates are exactly the same. Okay.
I have a question, James.
Yes.
Now, do you remember in the beginning of the video when you presented a little tub of minerals to me?
Yes.
And a lot of them had very different colors.
Yes.
But they were all the same.
Yes.
What if we did a streak test
Yes.
on all of those minerals? Would we see... What would we see?
Well, we had pyrite, remember? We said a pyrite, we've just
Yep.
shown you the streak. And that brings us to a very good point, okay? You'll remember the other 5 were quartz. Quartz here. Now, we know, I know and you know, that quartz has got a hardness of 7, okay? So the question would be, let's go back to, we spoke about this when we, about 15 minutes ago. If I was to take a piece of quartz and I was to use this on the streak plate, it scratches the streak plate, and I was to do the colour. Well, the colour is the same colour as the streak plate.
Yeah.
And that's because, and so students would get it wrong by saying, the color of the streak of quartz is like a sort of like a light grey, white, off-white color. That's not what you're looking at. Is you're looking at the color of the streak plate.
Because these minerals are harder than the streak plate. Okay.
So I hope that makes sense as to why we don't use streak plates for hardness. Okay, we just go as far as the glass plate, so it's got to be harder than 5.5.
Right.
And if it's harder than 5.5, we do not use a streak plate. That's basically what we tell the students.
So we can't do streak.
We can't. However, saying that is that if I have a piece of calcite, which is, because calcite can come in different colours as well. If we have a piece of calcite which is like a yellowish colour, we've got another one which is like a greyish colour, and one which is pure white, all will have the same streak.
Okay, so it's important when you're curating lessons like this to really be mindful of the samples that you're using, and that students can actually get the results that are expected.
Absolutely.
Okay.
And again, this is why the Rock and Mineral Lending Library has got all of these different minerals in perfect condition, nice big samples, and so you can show all these properties really, really nicely. Right, that was streak. Cleavage and fracture. We are going to first of all concentrate with my favourite mineral, or one of my favourite minerals, calcite. Okay, this is the nice piece of calcite. It's a nice clear one just through here, and we are going to explain what cleavage is. Okay, cleavage is, if you look at the crystal ball just over here, this crystal ball here, it's broken, so it's not very good for predicting the future. So, but it was very good for us because I managed to get this really cheaply from a new age shop because it had been broken. And what you can see is, can you see there are predefined lines of weakness in here? Okay, see it over here as well. This is a beautiful calcite crystal. Yeah. There's a line through here, and there's more lines going through here, and more lines going through here. When you get your eye in, you can actually see they are running parallel to this crystal edge here, okay?
Oh, wow.
If you really get your eye in here, you can see there's more lines, which are basically running parallel to this crystal edge. All the way through. Can you see this as well?
Yes, and I'm wondering, is it time to get the hand lenses out? Can you see them with the hand lenses?
And this is exactly what we do with the hand lenses. And one last thing is you can see, it's a bit difficult to see here, but you can see there's parallel lines running, basically, along parallel to this edge, okay?
Yep.
Now, I'm going to show a video in a moment which is showing you me smashing a piece of calcite. And when you start looking at the smashed pieces of calcite, notice how it's a rhomboidal shape here, and then look, there's rhomboidal shapes here.
They're like little clones.
It's almost like Inception mineral.
Yes,
there's a mineral within mineral within mineral. Now, what we do as part of the kit is we supply you with pieces of calcite. So I've got a nice piece here, and I'll give you that piece there, and I've got a nice piece here.
It's that rhomboid structure, it's very, very, sorry.
That's
that
right,
rhomboid structure is very, very clear in this.
Now, the best way to show cleavage with students is to look at the broken edges of the mineral. Can you see the broken edges here? And just like that.
Yes.
Yeah. You can see it's got like a step shape into it, okay?
Yep.
We now take our hand lenses like this.
Oh, I can see some of those parallel lines.
Yeah. Not only do you see the parallel lines within the crystal itself or with the mineral itself, but when you look at the broken edges, they are beautiful, almost like 75-degree shapes. Can you see that?
Oh, yeah, absolutely.
So when you're trying to explain cleavage and fracture to a student, you must make sure they're using a hand lens. It's the only way you can really see it clearly. And also, as I've said before, and I'll keep on banging on about this, is that the minerals that we include in the kits show these beautifully, okay? If you were just to get a piece of calcite from a shop, it probably wouldn't have that beautiful shape to it.
Can I just say too, watch out if you're going to buy minerals like at museums and things like this. You know, they might not have the mineral displayed, you know, with a natural cleavage. It might be polished. It might be polished into some kind of shape.
Yes, exactly.
also injected with color, which makes for something very beautiful, maybe for your home, but not great for a science class.
Yeah, no, I absolutely agree. Yeah, I mean, you get lots of fake minerals out there, which is really frustrating because you see them being advertised and it's like, no, it's not what it is. It may say it's a piece of calcite, but it just might be a piece of quartz. Because they look very similar, but they got very different properties, which is part of what we're doing here, okay? I've actually got lots of broken up pieces of calcite here as well. So what you can do is you can show the students this rhomboid structure just here. And when you use a hand lens, you can actually see, look at that. It's very cool. So we actually include broken up pieces.
Oh, wow.
So you can actually see those rhomboids, that inception rock, or sorry, inception mineral idea we spoke about. It's actually really perfect to see there, okay?
I'm just thinking if you had one stereo microscope, that would be a great, sample to put onto the stereo microscope, maybe have a larger sample side by side to maybe do some comparing and contrasting.
Yeah.
I mean, you don't need a stereo microscope. It's just... I think it just plays to the role playing of being in a science class and the excitement of maybe applying some of those microscope skills that students may have learned. But really, really clear. Thanks, James.
No worries. That's cleavage, okay? On the other thing, just to point out, with cleavage planes, when the light shines off, can you see just there, right there, the whole of the side of that mineral goes into a reflection at the same time, okay? That is a cleavage plane, okay? We can do the same thing here. Can you see how it all goes in, reflects at the same time? See that? And the third plane is at the bottom here. Okay, this is a really nice way. There we go. So when you have a crystal side like that going at the same time into that almost like a shininess, I suppose. I don't like using the word shiny, but go shiny, is that we know we actually have a cleavage plane, okay? So we can say that this piece of calcite has 3 cleavage planes. It's got 1, 2, 3. You're looking for parallel lines which are repeated within the mineral, okay? It's tough to see sometimes, which is why we make sure the minerals that we give out to schools are, and also what we teach our undergraduates with, have to be really good at showing these features.
Can I ask a question?
Of course you can.
Is it useful to put some text behind here to see the refraction?
It is indeed.
Does that help with when you talk about cleavage?
No.
No.
No, it doesn't.
Okay.
But it doesn't. But it does show you another property of, it's a bit, you probably can't see that unfortunately, but basically it's double refraction. Calcite, and it's a nice clear piece. You'll see double, it's a bit difficult.
So if you've got something that's relatively transparent, it might make a nice bridge between a unit and light where you're discussing reflection and refraction.
Yeah, absolutely. So that is cleavage. Back, I'll quickly show the video I did, and you can do this as a demo in class as a teacher, is if you get a nice piece of calcite, is you can do this. Now, I stupidly used a mortar and pestle, but a hammer works better, and probably best not to do it on a table. But as you can see, there we go.
Wow.
And if I break it even more, this was a very stubborn piece of calcite here.
Beautiful breaks, though, which
look at
really
perfect.
demonstrate.
Yep. It's predefined lines of weakness. They all have that rhomboidal shape. That was cleavage. Fracture. Okay. Fracture's a hard one, okay? And we're going to use quartz to show fracture because quartz is a nice sample to do it on, okay? When you've broken a window, you might see this shape here. This is called fracture. And this particular type of fracture here we call conchoidal because it looks like a shell. Now, if I look at a glass plate, which I will do in a moment, and look at the broken edges, you will see that beautiful shape being broken, okay? But what I want you to really appreciate is that this is a beautiful quartz crystal, okay? And when you first look at it, and students often think of this, they'll look at a piece of quartz and they'll go, oh, look at those really nice lines here, okay? Oh, look at this beautiful shape, that's cleavage. That's not cleavage. That is habit. Habit is the way the crystal grows, which is why it's important for you to look with a hand lens and see if there is predefined lines of weakness, if these lines here are repeated within the mineral.
Okay, so habit is like the form of the crystal as it's growing. Cleavage is
how it breaks.
How it breaks. Okay,
and how it breaks in a particular way that it has those predefined lines of weakness, which means that you always see that same shape repeated if you bash it with a hammer.
And then what's the difference then between cleavage and fracture?
It's cleavage and fracture. It's just a way of identifying minerals.
Okay, so could you say cleavage is the larger idea and then fracture is the smaller?
No, they're kind of the same but different, I would say, because it's literally how does the mineral break? Does it break with when you hit it and it breaks, does it go into a specific shape, or when you hit it, does it just go splinter almost? Okay.
So is a fracture?
Fracture is almost like splintering.
Okay, got it.
That's how I like to explain it.
Okay.
Let's actually look with a nice piece of quartz here, some vitreous or glassy quartz, and the way we see, we can see it's got a beautiful shape to it, and the reason it's got a beautiful shape is it's grown in that way, okay? If you want to know if it's cleavage or fracture, what you want to do is get the hand lens out and look at a broken edge, and look at that piece. Have you got anything?
I think I can see a fracture.
Look at that one in particular.
Okay.
So look at the broken bottom part.
Okay. It doesn't look regular to me.
It's completely irregular.
I can see a conchoidal.
Yes, the conchoidal fracture. Now you can either look at the bottom part of the crystal, where it's broken off the main part, or look at the tip.
Okay.
Look at the tip. And if you look at the tip, you should notice, where it's broken on the tip, it looks like fracture. It does not have that sharp boundary that you would expect to see if you had cleavage. Can you see that?
Yeah, I can, absolutely.
So the way we explain to the students is that the shape of the crystal can either be cleavage, or it can be the way the crystal's grown. It's the habit. Okay? And so the way to make sure you distinguish between those is by looking at the broken edges. And these are really nice samples because when you look at the bottom in particular, you can see it's very murky. There's no predefined lines of weakness in there. You can see there are some lines in here, but that's just the way the crystal grew. Okay?
Okay.
So cleavage and fracture, it can be tough, especially if you're trying to explain it, that you can see predefined lines of weakness within this calcite. And when you break it into smaller pieces, that same structure, that same shape is replicated. So for the calcite, we can say there's 3 planes of weakness or 3 cleavage planes, and they are at 75 degrees to each other.
Just have a look at some more mineral samples.
Yes.
And try to practice and see what I can come up with, and obviously use some resources to check my understanding of that.
Yeah, absolutely. I mean, the more that you look at this, the better, I think. And when we're going to have 5 unknown minerals that the students will do, we won't do that in this video because I think that's something you can play with. What we might do is another video where we go through all of that. But those 5 minerals that you look at, you're going to be looking at cleavage versus fracture in each of those.
And I would say, educators, if you have the opportunity to have a look at those resources, maybe have a go on your own first.
Oh, absolutely.
Then watch the video and see how you went. Yeah. Because you might find that you do actually know and can follow along quite well. And then just having that experience as a student will draw out some of the questions that your students themselves might have. And you can think about a way to respond to them.
But I would always say make sure you use a hand lens when you're looking at cleavage and fracture because it will really help you. There's some other properties, of course. Smell. Yeah. So if you smell a piece of sulfur, smell that. Oh. Bring back memories.
Oh.
so
Volcano.
Volcano, that's right. So if I'm sniffing this, we know this is a piece of sulfur. Okay. Tell by that. Taste. Now we don't get students to taste the minerals. That would be cray-cray. So we won't be getting them to taste it. But for instance, if you had some halite and you tasted the halite, it would have that salty taste to it.
Yeah. Okay. So you really want to be careful about introducing taste into the science. At home, you've got table salt, sodium chloride. What's the geological term for sodium chloride?
Rock salt.
Rock salt, something like this. They can certainly taste it.
The other thing you can use is fluorescence. Just be aware that UVA and UVB are both ultraviolet, and sometimes you may get a UV reader which is only doing one or the other. So I always thought, and it was only recently I found that out, that so sometimes some minerals that do fluoresce under certain conditions with a UV reader might not actually fluoresce. So just be aware of that.
There's some wonderful, very cost-effective fluorescent lights that you can get for the science lab too. And I remember that the last school I was working at, we didn't have a class set. We ordered a couple of them, and we would use them at stations with rocks and minerals that do fluoresce.
Yeah. Magnetism as well. It's magnetism you can use. The other one you can use is acid. And so let's look at, this will be a teacher demonstration, but we have a piece of calcite just there. What we'll do is we've got some 3% hydrochloric acid, it's just here, and I've got a piece of calcite here, and if I put just one drop on, it might be difficult to see, but would you like to have a look at that?
Oh, I can hear sort of a fizzing, and I can see there's an evolution of a gas.
Yes.
So there's certainly a chemical reaction happening with the dilute hydrochloric acid on the calcite.
Yeah, and I can see it's fizzing as well. Yeah, so there's lots of little bubbles coming off. And that is what happens when you put a carbonate with an acid.
Very useful, small, simple demonstration if you're going to be doing a unit in chemical reactions as well. But quite a complicated reaction for middle school or junior science, but nevertheless quite exciting and something that you might use as a bridge between chemistry and geoscience.
Awesome. Okay. The last couple of things is just we do with students is a summary sheet. Just tell them it's the basic blocks of geology, what minerals are. We've looked at colour, hardness, luster, streak, and the terms cleavage and fracture. And then what we do with the students is we say to them, okay, we are going to identify 5 unknown minerals. This will be a separate video for you to watch. This is basically the mineral sheet we give the students. Now notice that the first unknown mineral, and as a teacher you will have the correct answer to these, it has under streak, not applicable because the mineral hardness is greater than 5.5.
Oh, I think I know what it is.
So anyway, what we tell the students is that yes, when you're looking at these unidentified minerals, the first 2 we give them, they've actually looked at as part of the demonstration of how we identify minerals. And the reason we do that is the first 2 are ones they've seen before, they're comfortable with them, they're familiar with them. You might hear the first group of students going, oh yeah, we saw that before, it's a piece of quartz. That isn't the right answer. The right answer is for them to do the 5 tests, well not 5 tests because we've already told them not to do the streak because the mineral is harder than 5.5. But what we do want them to do is to be able to reconfirm and just establish that they are doing those 5 different tests correctly. And
that's okay because, so mineral ID number 1 might be more confirmation style investigation, whereas minerals 2 to 5 can be sort of a different type of inquiry. I like to think of a quote I read from a paper a little while ago about geology, and it said, no geologist went out into the world and then checked the textbook.
I like that. Yeah.
However, students in this activity are engaging in a bit of a confirmation investigation, and then they are working as a geologist might to identify some important minerals in perhaps their local area.
All right. And the last thing as well, and as I said, we'll do a separate video for this. Basically, be looking at how we do those 5 different minerals, just for a teacher, so the teachers can see how we do the 5 minerals and to check their understanding and learning as well, to make sure that you're happy to do this in the classroom. But we just wanted to show you that we actually use a flow chart here when we are with the minerals, okay? So you'll see that there are 6 minerals at the bottom. We've got feldspar, quartz, calcite, muscovite, amphibole, and biotite. 5 unknown minerals are represented there. We put a 6th one in just to make it a little bit more difficult, but they will only be looking at 5. And for the purposes of the assessment, we use this flow chart. We try to do this so that they've got some kind of visual representation of how they would determine what the actual mineral is. I think there's time for us to sign off now. We hope this has been useful. I know we've gone into a lot of detail, but I hope that that's helping you to cement your understanding as a teacher or an educator when you're coming to try and explain this in the classroom. Anything you want to add?
No, just to say that it's been a pleasure to present to you today, and we hope that you can take something away from the video, whether it's being better able to identify minerals through certain properties that we've discussed, or also knowing about a little bit more about how to stock your prep room or source some resources for geoscience.
And so the rock and mineral kits are available from the Geological Society of Australia. I've already put my email address right at the beginning of the presentation on slide number 1, but just for reference, it's james.driscoll@monash.edu. If you are from overseas as well, contact us, because we can give you some advice on where to get minerals from, or what you actually need in the kit as well. That's useful as well. But yeah, happy to take your messages.
By the way, I'm heading to Adelaide in a couple of weeks. Can I take one of those kits?
Of course, love to.
Fantastic.
Awesome. Thanks everyone. Take care. Bye.